When we decided to build a house, we decided we wanted to do it in a quote-unquote green way. We had the house designed. We were thinking geothermal would be a good way to, use some of that heat and cooling from the earth. And then Tom, our architect, brought us this idea of a passive house design.
The basic concept of the passive house is to put your effort into the things that stay, the low-tech, simple, permanent elements of the house. The wall structure, the insulation, the airtightness layer. These things last. They're not gadgets, and they allow you to hugely cut your energy use by just good insulation and good orientation, good windows, good thresholds and weather stripping and all that kind of thing.
It's very common in Germany and Austria and some other European countries that the technology really does work, that we could have a house that's super insulated, has very low technology in terms of the heating, with a heat pump and a few other little bells and whistles. And they managed to convince us that this could be done, and it could be done making a house that we could A, afford, and B, that would fit our lifestyle as a family of four. These super thick walls and triple insulated windows and the kind of ceiling that goes on when you build a passive house means the temperature is comfortable everywhere in the house. It's draft free because it's so well insulated. Everything is very well sealed. The windows are triple pane. There was double, triple sealing of everything, including the basement. Even the basement is insulated. That's not drafty. It's very comfortable down there. It's all usable space. The kids can play down there. We can watch TV down there. My husband can have his office down there, and everyone is comfortable. So it's a great use of space when you have a house that's not drafty and it's very, very comfortable. The other advantage is that it's constantly ventilated, so the air is fresh, probably fresher than in a normal house where, say you had a lot of cooking fumes or something, or you had a lot of people over, it might get stuffy or stinky, and we don't really have that problem.
Yeah, the ventilation system works by exhausting from all the areas where moisture is made. So kitchen, bathrooms, laundry, and when you suck those out, you're basically sucking out indoor pollutants. And that goes into the heat recovery ventilator, which is about a 90% efficiency at taking that heat that is traveling in that air on the way out and putting it into the incoming fresh air, which today is about 20 degrees, 25 degrees. So it gives us 90% of the heat to that incoming air, which is fresh, and that fresh air is running constantly. And that's giving us about 0.3 air changes an hour. So in other words, the air inside the house is exchanged with fresh air once every 3 hours. That's much higher than a typical house. Under the stair here is the mechanical room, and I can show you the energy recovery ventilator, which is this device right here. So an energy recovery ventilator is a lot like a heat recovery ventilator. It's sucking warm air out of the house from the moist areas, and it's bringing fresh air in from the outside continuously. This is an airtight house, so we need to have it breathe. We want to have it breathe in a smart way, not breathing just randomly through cracks in the envelope. So this is our nostril of the house, let's say. It's about 90% efficient. It's made here in the US. This is one of the passive house type components we can get. Sterling Technologies, it's the ultimate air recuperator. It's a great unit. And this is the incoming air from outside. You can see we have here a little, what's called a defrost coil. It's a little electric coil so that when it gets really cold out there, we don't want that cold air coming in and freezing on that desiccant wheel that's that's moving in there. It's the filter wheel basically. That freezes up, this thing doesn't work. So this, when it gets really cold, will kick on a little bit, heat that just enough so that it doesn't freeze in there. Then this is the exhaust air heading out. These ducts are insulated, vapor tight, continuously from the unit all the way out so that we don't have condensation, we don't have problems with heat loss in this room. So from there, the air moves into the inside, coming in like so. Actually, this is the supply back here, and it's coming in and it hits the fan unit of our mini split. The mini split is basically a tiny heat pump that will provide some supplemental heating when we need it and cooling in the wintertime. There's enough humidity in this climate that we want to have the ability to dehumidify and cool a little bit, so that heat pump can give us that heating and cooling. So it's compared to a conventional 100,000 BTU furnace, we're talking about something less than a tenth that size. So it's not, there is heating that needs to happen in a passive house. It's not a conventional furnace. It's not a big honking energy hog.
When we first heard that we could build a house without any furnace at all, we thought that was crazy in Chicago to have a house without a furnace. We were pretty incredulous.
So this is the compressor for the mini split heat pump. So all the heat and cooling that we need typically is coming out of this guy. It's very quiet. You can hardly even hear it's running unless you get up close to it. Very efficient, super efficient.
We can also control the ventilation. There's a knob on the wall, so if nobody's home and we don't need a lot of fresh air, we can turn it to low. If we're having a big party, there's a lot of cooking going on, we can turn it up. So normally you can't control that kind of thing in a house unless you open a window or a door.
Passive houses are very quiet from the outside noise because the walls are super thick insulated and the triple pane windows keep that noise out. So interior noise you're more aware of. And we have to be careful about acoustics when we're designing these mechanical systems. So the units that provide they have fans in them, we want to isolate from vibration. And then this right here is a little muffler so that any vibration that's in this duct is not transferred to this duct. You can hear the fan noise here in the room with the ERV running on medium, but you pretty much can't hear it in the house at all. I'm going to shut the door here and we'll just turn off the light and see what it's like. We're just right across the wall from it and you virtually can't hear it at all. So it's very, very quiet. It was one of the considerations that the client had. They said, well, if there's continuous ventilation going, are we going to hear it? And you don't hear it upstairs at all. Part of the idea was with this super low energy, super well insulated, super airtight house, we hardly need any heat to heat it. But when it gets really, really, really cold, we'll need to supply a little bit of heat, and our heat pump that we have for typical days won't want to work because if it gets down below zero, that heat pump stops being efficient, it stops functioning. So we need another source of supplemental heat. And we have two of them. We have this guy, and we have a couple little electric sources. We have a tile heat under the tile heating mat in the master bath and the kids' bath, and a little electric heat coil in the incoming airstream. So these things won't need to be used much, but when it gets really, really, really cold, they're there. So that's another one of the sort of functional reasons we chose the pellet stove.
We don't necessarily need this pellet stove, but since we weren't going to have a fireplace because of the heat-losing properties of a chimney, we decided we want some kind of a fire feature in the house, just to make it cozier and more traditional. I think people like some sort of a fire, centerpiece of fire in their house somewhere, and some kind of a hearth, And so we decided to go with this pellet stove, which this one is only designed to heat one room of a house. It's a very small pellet stove, but because our house is so well insulated, when it does get extremely cold out, we could heat the whole house with it, apparently.
These are what the pellets look like. That the pellet stove burns, and you open the little hatch here, and you take a bucket or whatever you've got, and you pour them in, and you just fill up that hopper every however often you use it, a couple of weeks or something like that. And it has a thermostat switch back here, and this thing can modulate up and down. It can give you a lot of heat or less heat. I forget exactly what the BTU rating is. I think it goes from about 10,000 to 20,000 BTUs, something in there. So if we have it on high, it'll definitely overheat the house, even on an extremely cold day. Which, to put that into perspective, a house like this, if it was conventionally insulated and everything, would probably need well over 100,000 BTUs. So we're talking about a tenth of the energy demand for space heating. When we designed the house, we have this 3D modeling software that allows us to position the house geographically, and we also modeled the neighbor houses so we could see it and we could cast shadows. We had to be able to predict what the solar effect would be of the neighbor to the south and the sunlight. So you can see it right here. It's just like the model. We're at December 5th today, and we're about noon, so this is sort of getting close to our worst case scenario, the sun being lowest in the day, or lowest in the sky. And you can see how the windows were placed the bedrooms were placed all to the south, so that they could have big windows and take it in. You know, it wouldn't make sense to put the bathrooms there where you want small windows. So the house is arranged to take advantage of the sun. And then up at the top, you can see that clear story, which is grabbing that light and putting it down into that north side stairway and bouncing that light down into the house. And also the heat. It's a lot of heat gain, even though it's cold time of year, low sun. Well, these are the best windows we could get from North America. They're low-end triple pane wood windows, and they have a high solar heat gain coefficient, which means they let a lot of heat through from the sun to warm up these guys. One of the things that we need to look out for in windows is that we're not losing a lot of heat through the frames, because that's where we lose most of the heat. So we try to use larger panes, fewer of them, and join them up with other windows. You can also see in this just how deep the wall is. That's the thickness of the wall, about 12 inches.
So there are 4 energy-saving devices in this house that are kind of unusual. One is the induction cooktop, which is about 85% more efficient than a traditional stove. It cooks by sending a magnetic disturbance through your pot, so it doesn't actually create heat. It's also very easy to control the temperature with an induction cooktop stove, because you can go to a very low setting or a very high setting.
This water heater has a heat pump on it. It can take heat out of the air and put it into the water. So it runs a little more efficiently, because otherwise the heat is coming from an electric source. So we try to use a more efficient source, which is the heat pump. So it does suck some heat out of the air, and Mary Chris's idea was that you could just hook that up to your refrigerator, which is dumping heat into the air so you can make it cold in the fridge. Then you'd have two things that work together, but that's a future invention. Meanwhile, this will make it a little cooler down here, but not remarkably so. In the summer, on the other hand, it's more like a little mini air conditioner, because it's helping cool the house, putting that heat into the hot water. So this is a storage tank, and then it just runs from there up to the fixtures.
Another unusual feature of this house is the condenser dryer, which does not vent to the outside. Instead, it actually condenses the water and sends it out along with the other wastewater in the house. It does not continually blast hot air at the clothes, which means that it's a lot more energy efficient. It just heats the air inside of the dryer and tumbles the clothes. And it takes a little longer to dry. It takes about 2 hours to dry a load, but it's so much more energy efficient that we found that it's really worth just waiting a little longer for your clothes. The drying rack is a really low-tech feature that anybody can pick up at their local Target or Container Store. I found that it's great for drying clothes, partly because it doesn't wear your clothes out so much, and
super low energy.
Super low energy, and it also creates a little nice humidity. Normally, with a house you have this thermostat and you just set the temperature and you leave it and you forget it. But here, because the house works so slowly in adjusting temperature, you have to spend a lot of time experimenting. It takes a while for a house to heat up or to cool down because the technology, it's not a blast furnace, and it's not an air conditioner blasting cold air. So it's I compare it to driving a sports car versus turning a ship, where you kind of have to plan ahead and be patient while the temperature adjusts.
So there are certain criteria that we need to fulfill for a house to be a certified passive house. You have to have a heat demand, a yearly heat demand under 4.75 kilobTUs per square foot. And the same is true for the cooling. For the primary energy demand, it has to be under 38 kilobTUs per square foot, which means primary energy demand versus site energy is an important difference. A lot of people will talk about how they have a zero energy house, but they're talking about zeroing out or compensating for the energy that they use here. But when you talk about electricity, you really need to talk about primary energy, because primary energy takes into account the kind of fuel you're using to create the electricity. For instance, if you're talking about electrical demand. So in our case, it's mostly coal, which is got huge greenhouse gas emissions. And there's a lot of loss at the plant where you're burning the coal and turning it into electricity. And there's tremendous line loss, resistance getting from the power plant to here. That's about a 3.5 times multiplier. So we have to take that into account when we do our calculations, and the software that we use for designing passive houses allows us to do that and to see what our real carbon footprint is of the house. And we can also calculate how much energy on-site renewables we would need to offset that, so we can figure out how to make a true zero energy house. Passive House is very interested in reducing carbon and creating houses that people can afford to heat and cool and light and live in, comfortably. So the other criteria that needs to be met is the air tightness has to be less than 0.6 air changes per hour when it's pressurized to 50 pascals. So we're talking about 10 times more airtight than code. So on this house, we did not quite make a few of those critical criteria. The air tightness is 1 air change per hour instead of 0.6, and our space heat demand is a little higher than that 4.75. I think we're about 15% over. So it's functionally operating as a passive house, but it is not to this point of certification.
We also like the idea of just being pioneers and demonstrating to people who live in the Chicago area that this is possible, because it's not really a well-known concept in this area of the country, even though it offers a lot of hope for significant energy savings and reduction of global warming. So we hope that this will help educate people about the technology and the possibilities that are available.